Welcome to our lecture on Group 2 elements, commonly known as the alkaline earth metals. We will be exploring beryllium, magnesium, calcium, strontium, and barium. These elements share a defining characteristic. Their outermost electronic configuration is always ns2, meaning they have two valence electrons in their outermost s orbital. For example, beryllium ends in 2s2, while magnesium ends in 3s2. We will start by investigating the general trends in their physical properties. As we move down the group from beryllium to barium, we observe predictable variations in several key areas, including atomic and ionic radius, ionization energy, standard electrode potentials, melting and boiling points, density, and hydrated radius. Let's break down each of these properties one by one. Let's begin with atomic radius. The size of an atom is governed by three main factors: the number of energy levels, which creates a screening effect, the nuclear charge pulling on valence electrons, and the penetrating power of those electrons. The clear trend here is that the atomic radius increases as you move down the group, from 0.089 nanometers in beryllium to 0.198 in barium. You might wonder why the radius increases, even though we are adding more protons to the nucleus, which should pull electrons closer. As we move down the group, a completely new inner energy level is added each time. This creates a massive screening or shielding effect. This screening effect completely outweighs the increased nuclear charge from the extra protons, resulting in a weaker pull on the outermost electrons and a larger atomic radius. Next is the first ionization energy, which is the energy required to remove the outermost electron. This is governed by factors like atomic radius, nuclear charge, and the screening effect. The data shows a distinct trend. The first ionization energy decreases as we move down the group, dropping from 900 kilojoules per mole for beryllium down to 502 for barium. The explanation for this decreasing trend is closely tied to the atomic radius. Because new inner energy levels are added down the group, the screening effect increases dramatically. Just like with the atomic radius, this screening outweighs the added nuclear charge. Since the outermost electrons feel a much weaker pull from the nucleus, it takes significantly less heat energy to strip an electron away from a barium atom compared to a beryllium atom. Moving on to standard electrode potential, or SEP. This property is governed by three main energy changes: atomization energy, ionization energy, and hydration energy. The trend here is that the SEP values become increasingly negative as we move down the group, starting at negative 1.85 volts for beryllium and reaching negative 2.90 volts for barium. To understand these values, we must look at SEP theory. The electrode potential measures the ease with which a species is reduced compared to hydrogen. Because the values for group 2 metals are negative, it tells us they sit above hydrogen in the electrochemical series. This means they strongly prefer to undergo oxidation, losing electrons, rather than reduction. The increasingly negative values down the group show that reduction becomes harder and oxidation becomes easier. To understand why oxidation becomes easier down the group, we must break the overall oxidation process into three distinct energy steps. First, the solid metal must be turned into a gas, which requires endothermic atomization energy. Second, electrons are removed to form a gaseous ion, requiring endothermic ionization energy. Finally, the gaseous ion is dissolved in water, releasing exothermic hydration energy. As we move down the group, both the atomization and ionization energies decrease, which makes forming the ion easier. While the hydration energy also decreases, which normally makes ion formation harder, the drop in the first two energies is much larger. Therefore, the overall oxidation process becomes easier down the group. Note the beryllium anomaly. Its extremely small radius gives it such a high ionization energy that its oxidation is much less favorable than the rest of the group. Now, let's examine atomization energy. This is the energy required to produce 1 mole of separate gaseous atoms from the solid metal. The trend generally decreases down the group. Why? Because as the atomic radius increases, the delocalized electrons are further from the nucleus. This weakens the nuclear attraction and, consequently, the metallic bond, meaning less energy is needed to break the solid structure apart. Similarly, the melting and boiling points generally decrease down the group. The reasoning is identical to atomization energy. A larger atomic radius means the delocalized valence electrons are further from the nucleus. This weaker attraction results in a weaker metallic bond, so less heat is required to melt or boil the metal. However, you will notice some irregular spikes in the data, particularly around calcium. You may have noticed those irregular patterns in the melting and boiling points. These are caused by changes in the crystal structures of the metals. Beryllium and magnesium pack in a hexagonal close-packed structure, but calcium and strontium shift to a face-centered cubic structure, and barium uses a body-centered cubic structure. These shifts in how the atoms physically pack together create distortions that alter the strength of the metallic bonds, causing those data irregularities. To summarize metallic bonding, the strength is proportional to the number of delocalized electrons divided by the atomic radius. This explains why group 2 metals are significantly harder and have much higher melting points than group 1 alkali metals. Group 2 metals contribute 2 delocalized electrons per atom instead of 1, and they have smaller atomic radii. Combined, these factors create a much stronger metallic bond. Let's shift our focus to the hydrated radius. Interestingly, the trend here is that the hydrated radius decreases down the group. As we move down, the actual ionic radius of the bare ion increases. Because the charge remains a constant +2, this larger size means the charge density drops. A lower charge density means the ion has a weaker attraction to water molecules, so it gathers a smaller shell of water around it. Next, we look at density. The density of group 2 elements generally increases as you move down the group, from 1.85 for beryllium up to 3.62 for barium. This happens because as we move down, we add protons and neutrons, massively increasing the atomic mass. While the atomic volume also increases, the jump in mass is much greater, resulting in a higher mass per unit volume. However, you will notice a slight dip in density from beryllium to calcium. In this specific region, the rapid increase in atomic volume actually outpaces the increase in mass, causing the density to temporarily drop before rising again. Understanding these densities is crucial in industry. For example, higher density metals are much better at absorbing radiation, making the heavier elements excellent candidates for shielding. Let's apply these concepts to some real-world scenarios. Imagine students building a solar water heater. They need materials with specific thermal properties. By analyzing the melting points, which decrease down the group, they can select the right metal. In another scenario, a company producing alloys must understand atomic radii. Because the radius increases down the group, chemists can predict exactly how these different sized atoms will physically pack together in a new alloy. In a third scenario, civil engineers might need materials for radiation shielding in construction. By looking at the density trend, they can see that barium, with the highest density of 3.62 grams per cubic centimeter, is the most suitable group 2 element for blocking radiation, thanks to its high mass-to-volume ratio. Now that we understand their physical properties, let's dive into the chemical properties of group 2 elements. They're very reactive, though slightly less so than group 1 metals, because group 2 atoms are smaller and hold on to their electrons tighter. Within group 2, reactivity increases as you go down the group. This is driven by the increasing atomic radius, decreasing ionization energy, and increasing electropositivity. When heated, these metals react readily with dry oxygen in the air to form normal metallic oxides. Following the equation, 2M plus O2 yields 2MO. However, under prolonged heating, the heavier elements behave differently. Barium, and to a lesser extent strontium, will actually form a peroxide, represented as BaO2. You might wonder why only the heavier metals, like barium, form peroxides. It all comes down to charge density. The peroxide ion is held together by a weak covalent bond. Small cations at the top of the group, like magnesium, have a high charge density. They strongly polarize the peroxide ion, ripping that weak bond apart to form a normal oxide. But large cations like barium have a low charge density, so they don't distort the peroxide ion, allowing it to remain stable. Finally, let's look at their reaction with nitrogen. Nitrogen gas is notoriously unreactive due to its strong triple bond, but group 2 metals are reactive enough to combine with it when heated. They form metallic nitrides, consisting of M2+ and N3- ions. We will explore more of these fascinating chemical reactions as we continue. Picking up where we left off, let's look at how these metals interact with nitrogen. Nitrogen gas is notoriously unreactive because of its incredibly strong triple bond. However, group 2 metals can force a reaction. Because they form divalent 2+ cations, they have a very strong attraction to the 3- nitride anion. This results in a massive lattice energy, making the formation of group 2 nitrides highly exothermic and stable. In stark contrast, group 1 metals, which only form 1+ ions, don't generate enough lattice energy to overcome the nitrogen triple bond, making their nitrides endothermic and unstable, with the sole exception of tiny lithium.
To understand exactly why group 2 nitrides form so readily, we have to look at the thermodynamic energy balance. Creating a nitride requires a lot of energy input. You have to atomize the metal, strip away its electrons, break the nitrogen triple bond, and force electrons onto the nitrogen atoms. All of these steps are endothermic. The only way this reaction happens spontaneously is if the energy released at the very end, the lattice energy, when the gaseous ions snap together into a solid crystal, is large enough to outweigh all those initial energy costs. For group 2 metals, their high charge density ensures this lattice energy is massive.
Beyond nitrogen, group 2 metals also react directly with a variety of other nonmetals when heated. If you expose heated magnesium to liquid bromine, for instance, they combine directly to form solid magnesium bromide. They react similarly with sulfur to form sulfides. When it comes to hydrogen, the heavier metals, calcium, strontium, and barium, will react to form metallic hydrides, whereas the lighter elements in the group require indirect methods.
Moving on to reactions with water, we see a very clear trend. Reactivity increases as we move down the group. Beryllium stubbornly refuses to react with water at all. Magnesium barely reacts with cold water because it quickly forms a protective layer of magnesium hydroxide. But if you blast heated magnesium with steam, it reacts vigorously to form magnesium oxide and hydrogen gas. The heavier metals, calcium, strontium, and barium, readily react with cold water to form metal hydroxides and hydrogen gas, with barium being the most vigorous.
When it comes to dilute mineral acids, the story is quite straightforward with hydrochloric acid. All the group 2 metals, from beryllium down to barium, react to form their corresponding soluble metallic chlorides, liberating hydrogen gas in the process. Just like with water, you will observe that the vigor of this reaction steadily increases as you move down the group. Sulfuric acid, however, introduces a fascinating complication: solubility. Beryllium and magnesium react nicely because their resulting sulfates dissolve in the water, exposing fresh metal. But as we move down the group, the sulfates become less soluble. Calcium reacts very slowly because calcium sulfate is only sparingly soluble. Strontium and barium are immediately rendered passive. The moment the acid touches them, an impenetrable layer of insoluble sulfate forms on the surface, completely halting the reaction. Nitric acid behaves differently because it is a very strong oxidizing agent. Usually, it oxidizes the hydrogen gas into water before it can escape. However, magnesium, along with calcium and zinc, are exceptions that can actually liberate small amounts of hydrogen gas from dilute nitric acid. Beryllium, on the other hand, is rendered completely passive. The strong oxidizing nature of the acid instantly creates a tough, inert layer of beryllium oxide on the metal surface. Because group 2 metals are highly electropositive and basic, you wouldn't expect them to react with basic alkalis, like sodium hydroxide, and for the most part they don't. But beryllium is the odd one out. Because it has a much lower metallic character, it is actually amphoteric, meaning it can act as both an acid and a base. If you heat beryllium with concentrated sodium hydroxide, it will dissolve to form a complex ion called sodium tetrahydroxoberylate, releasing hydrogen gas. Let's shift our focus to the specific compounds formed by group 2 elements, starting with the oxides. You can prepare these oxides, like magnesium oxide or calcium oxide, by thermally decomposing their corresponding carbonates, nitrates, or hydroxides. You simply heat them up, and they break down into the metal oxide and a gas. You can also just heat the pure metals in oxygen, though you have to be careful with barium, as prolonged heating will push it past the oxide stage to form barium peroxide. There are two major trends to observe with these oxides. First, their basic character increases down the group. Beryllium oxide is amphoteric, while barium oxide is strongly basic because the larger atoms lose electrons more easily, increasing their metallic nature. Second, their melting points generally decrease down the group. As the metal cations get larger, the distance between the positive and negative charges increases, weakening the ionic bond. Beryllium oxide is an exception. Despite being the smallest, its extreme charge density polarizes the oxide ion, introducing covalent character that actually lowers its melting point.
Next, we have the group 2 chlorides. If you need the anhydrous, or water-free versions, you must pass dry chlorine or hydrogen chloride gas directly over the heated metal. If you don't mind water being present, you can easily make hydrated chlorides by reacting dilute hydrochloric acid with the metal itself, or its carbonate, oxide, or hydroxide, which is a standard acid-base neutralization.
The chlorides show a fascinating reversal in melting point trends compared to the oxides. Here, melting points actually increase down the group. Why? Because the chloride ion is large and easily distorted. Small cations at the top of the group polarize the chloride ion, creating covalent character which lowers the melting point. As you move down to barium, the cation gets larger, its polarizing power drops, and the bond becomes more purely ionic and stronger. This covalent tendency is also why hydrated magnesium and calcium chlorides hydrolyze into oxides when heated, rather than just drying out.
Because the beryllium ion is so exceptionally small and highly charged, it severely polarizes the large chloride ions, making beryllium chloride predominantly covalent. It doesn't form a giant ionic lattice. Instead, when heated, it sublimes into a gas, and the molecules pair up to form a dimer, BeCl4. In this structure, two chlorine atoms act as bridges, sharing their lone pairs of electrons with the beryllium atoms to help them achieve a stable electron configuration. Now, let's tackle the solubility of group 2 compounds. To understand why some salts dissolve and others don't, we use a Born-Haber cycle. When a salt dissolves, you first have to put energy in to break the crystal lattice. That's the positive lattice energy. Then energy is released when water molecules surround the ions. That's the negative hydration energy. For a salt to be soluble, the energy released by hydration must outweigh the energy required to break the lattice. As we move down the group, the atoms get larger, meaning both lattice energy and hydration energy decrease. The trick is figuring out which one decreases faster.
Let's apply this to salts with large anions, like sulfates. Because the sulfate ion is so bulky, the lattice energy is already relatively low and doesn't change much as the metal cation gets bigger. However, the hydration energy drops off a cliff as the metal gets larger. Because the hydration energy decreases much faster than the lattice energy, it can no longer overcome the lattice energy at the bottom of the group. Therefore, the enthalpy of solution becomes less exothermic and solubility plummets. This is why magnesium sulfate dissolves easily, but barium sulfate is basically a rock.
Conversely, let's look at salts with small anions, like hydroxides. Here, the small hydroxide ions can pack very closely to the small metal cations at the top of the group, creating a massive lattice energy. As the metal cation gets larger down the group, this close packing is ruined, and the lattice energy drops drastically. It drops much faster than the hydration energy does. Because the lattice energy is falling apart so quickly, the hydration energy can easily overcome it. Thus, solubility increases down the group, making barium hydroxide much more soluble than magnesium hydroxide.
These solubility trends aren't just theoretical, they are incredibly useful in the lab for identifying unknown ions. If you add sodium hydroxide or ammonia to a solution, magnesium will precipitate out immediately because its hydroxide is the least soluble. On the other hand, if you add a sulfate or a chromate, barium will precipitate out immediately because salts with those large anions become less soluble down the group. By using these specific reagents, you can easily distinguish between the different group 2 metals.
Moving from physical dissolution to chemical breakdown, let's discuss the thermal stability of group 2 compounds. When we heat these salts, we aren't just melting them, we are trying to break their chemical bonds in a decomposition reaction. Stability is favored by high ionic character. If a bond has too much covalent character, it's easier to break with heat. The general rule is that for salts with large anions, like carbonates and nitrates, thermal stability increases as you move down the group. Let's look at the carbonates as a prime example of this stability trend. The carbonate ion is large and easily distorted. At the top of the group, the tiny beryllium ion severely polarizes the carbonate ion, weakening the bonds within the carbonate itself. As a result, beryllium carbonate is so unstable it decomposes at room temperature. But as we move down to barium, the large barium ion has very low polarizing power. It leaves the carbonate ion alone, forming a highly ionic, incredibly stable lattice that won't decompose even under strong heating. As we've seen repeatedly with its covalent chlorides, its amphoteric oxides, and its highly unstable carbonates, beryllium often breaks the rules of group 2. This brings us to the concept of anomalous behavior, the tendency of the first element in a group to act completely differently from the rest of its family due to its tiny size and intense charge density. We will explore the specific details of beryllium's anomalous behavior and its diagonal relationship with aluminum in the next section. Now, the qualitative analysis, starting with magnesium ions. With sodium hydroxide, magnesium gives a white precipitate of magnesium hydroxide, and it does not dissolve in excess sodium hydroxide, so it's not amphoteric in this test.
With aqueous ammonia, you again get a white precipitate of magnesium hydroxide, also insoluble in excess ammonia. The key idea is that both reagents supply hydroxide ions, and once the ionic product exceeds the solubility product, MgOH2 comes out as a white solid. A very important practical note is the effect of ammonium chloride. If NH4Cl is present, it suppresses the formation of hydroxide ions from ammonia, so the solution may never reach the Ksp needed to precipitate MgOH2. Magnesium also has several confirmatory tests. With carbonate ions, magnesium forms a white precipitate of basic magnesium carbonate, written as MgCO3.MgOH2. In practice, ammonium carbonate in the presence of ammonium chloride can prevent the precipitate because carbonate ions are reduced. Carbonate is partially converted to hydrogen carbonate through the ammonium equilibrium shown. With oxalate, magnesium oxalate is a white precipitate, but the condition given is important. It forms only in the presence of ethanoic acid, which controls competing precipitations. Finally, there's a classic phosphate test. In the presence of ammonia and ammonium chloride, adding phosphate gives a white precipitate of magnesium ammonium phosphate, MgNH4PO4.6H2O, and that precipitate dissolves in acids. For calcium ions, sodium hydroxide gives a white precipitate of calcium hydroxide, again insoluble in excess sodium hydroxide. But a major difference from magnesium is with ammonia. Calcium typically shows no visible change because ammonia is a weak base, and the hydroxide concentration stays too low to exceed the solubility product of CaOH2. For confirmation, calcium oxalate is a key test. After adding ammonia, ammonium oxalate produces a white precipitate of CaC2O4. It dissolves in strong mineral acids like hydrochloric or nitric acid, but it does not dissolve in ethanoic acid. This solubility behavior helps distinguish ions. Calcium phosphate is also a white precipitate and dissolves in acids, but not in sulfuric acid because calcium sulfate can form. Finally, potassium chromate gives a yellow precipitate of calcium chromate, but only from concentrated calcium solutions, and it dissolves in acids except sulfuric acid, and also dissolves in ethanoic acid. Calcium has a few more useful reactions. With carbonate ions, calcium forms a white precipitate of calcium carbonate. With dilute sulfuric acid, calcium gives a white precipitate of calcium sulfate. This is important because it hints at why sulfuric acid behaves differently with some group 2 metals. And similar to magnesium, calcium can also form an ammonium phosphate precipitate when phosphate is added in the presence of ammonia and ammonium chloride, producing CaNH4PO4.6H2O, which dissolves in acids. Now for barium. With sodium hydroxide, barium hydroxide can precipitate, but mainly from concentrated barium solutions because BOH2 is relatively soluble. With ammonia, the theory says no reaction because ammonia is weak, but in real lab conditions, a white precipitate often appears. The reason is not barium hydroxide, it's barium carbonate. Ammonia solution absorbs carbon dioxide from air to form ammonium carbonate, and even that small carbonate concentration is enough to exceed the very low Ksp of BaCO3, so BaCO3 precipitates. Barium gives a very characteristic white precipitate with sulfate ions. BaSO4 is extremely insoluble. It also forms BaCO3 with carbonate, BaC2O4 with oxalate, which dissolves in acids because oxalate is protonated, and barium phosphate with phosphate. Finally, potassium chromate gives a yellow precipitate of BaCrO4, which is a classic confirmatory test. It does not dissolve in ethanoic acid or sodium hydroxide, but it does dissolve in mineral acids except sulfuric acid.
It's worth pausing on the explanation for barium oxalate dissolving in acids because it's a common exam reasoning point. Barium oxalate is in equilibrium with Ba2+ and oxalate ions. When you add an acid, the oxalate ions are protonated to form oxalic acid, H2C2O4, which removes oxalate from solution. By Le Chatelier's principle, the equilibrium shifts to the right to replace the removed oxalate, so more solid dissolves. In ethanoic acid, there's an extra push because barium ethanoate is soluble, which also supports dissolution.
A quick comparison. Magnesium, calcium, and barium all form insoluble carbonates, so carbonate alone doesn't uniquely identify the ion. The details matter. Magnesium tends to form a basic carbonate precipitate, and the precipitate can be suppressed by using ammonium carbonate in the presence of ammonium chloride. Calcium forms CaCO3 readily. Barium forms BaCO3 extremely readily, so readily that even trace carbonate contamination, like the carbonate formed in ammonia exposed to air, can precipitate it. The revision items now ask for explanations, not just statements. For Group 2, learners often memorize trends, but the exam wants causes: metallic bonding for melting and boiling points, ionization energy and hydration for electrode potentials, lattice energy versus hydration energy for solubility trends, and then special cases like sulfate layers affecting reactions with dilute sulfuric acid. We'll go through each of these prompts in turn.
For the metals themselves, melting and boiling points depend mainly on metallic bonding. As you go down Group 2, the atoms get larger, so the outer electrons are further from the nucleus and more shielded. The attraction between the positive metal cores and the sea of delocalized electrons becomes weaker overall. Weaker metallic bonding means less energy is needed to separate atoms, so both melting and boiling points tend to decrease down the group.
Electrode potential is about how easily the metal forms ions in aqueous solution. Down Group 2, increased size and shielding reduce the first and second ionization energies, so the metal loses 2 electrons more easily. That pushes the standard electrode potentials to more negative values, meaning oxidation to M2+ is more favorable. Hydration enthalpy does become less exothonic as ions get larger, which would oppose ion formation slightly, but the decrease in ionization energy is the dominant effect in the trend described.
Why do many Group 2 salts become more stable down the group? A big part of the explanation is polarization. Group 2 cations are +2, so small ones like beryllium and magnesium have high charge density and polarizing power, which increases covalent character in compounds and can reduce thermal stability for certain salts. As you go down the group, the cations get larger, charge density drops, polarizing power decreases, and bonding becomes more purely ionic. More ionic lattices are often more thermally stable. The question also mentions that Group 1 salts can show the opposite trend in some cases. The key contrast is that Group 1 cations are +1, and polarization effects are weaker, so different factors can dominate their stability patterns.
Solubility trends come from a competition between lattice enthalpy and hydration enthalpy. Down the group, lattice enthalpy becomes less negative because ions are larger and attractions are weaker. But hydration enthalpy also becomes less negative because larger M2+ ions hydrate less strongly. For carbonates, the drop in hydration enthalpy is especially important, so the overall driving force for dissolving decreases down the group and solubility falls. For hydroxides, the decrease in lattice enthalpy down the group is large enough that it outweighs the reduced hydration, so hydroxides become more soluble as you go down Group 2.
The melting points of Group 2 chlorides increase down the group, largely because the bonding becomes more ionic. Beryllium chloride is strongly affected by the high polarizing power of Be2+, so it has significant covalent character and a relatively low melting point. As cation size increases down the group, polarizing power decreases, chloride ions are less distorted, and the chlorides become more purely ionic. More ionic lattices generally have higher melting points, so the melting points rise down the group.
This is a subtle but important point. In general, Group 2 metals become more reactive down the group because ionization energies decrease, so forming M2+ is easier. But with dilute sulfuric acid, the reaction can become slower for the heavier metals because sulfate salts become less soluble down the group. Calcium sulfate is only sparingly soluble, strontium sulfate is even less soluble, and barium sulfate is extremely insoluble. These sulfates can form a coating on the metal surface, blocking further contact with the acid and slowing the reaction even though the metal itself is intrinsically more reactive.
For the water reactivity question, beryllium is the one that shows no reaction with cold water, largely because of its protective oxide film and its relatively low reactivity. Magnesium reacts only very slowly with cold water, but reacts vigorously with steam, producing magnesium oxide and hydrogen. Barium is the one that reacts very vigorously with cold water, giving barium hydroxide and hydrogen, with noticeable heat and bubbling.
For definitions, anomalous behavior means the first element in a group behaves differently from the rest. Beryllium in Group 2 is the classic case. Diagonal relationship is the tendency for certain period 2 elements to resemble period 3 elements diagonally below them, because periodic trends compensate along the diagonal. For beryllium, the reactions that demonstrate its unusual behavior include amphoterasm of the metal and its oxide and hydroxide, the covalent polymeric nature of beryllium chloride, hydrolysis of beryllium salts to give acidic solutions, and the distinctive carbide chemistry, where beryllium carbide produces methane on hydrolysis. To explain why beryllium chloride behaves so differently from magnesium chloride, focus on polarization. B2+ is very small, so it has high charge density and strong polarizing power. It distorts the electron cloud of chloride ions, giving BCl bonds significant covalent character and leading to polymeric structures. Covalent, molecular, or polymeric compounds tend to have lower melting points and can dissolve in organic solvents like ethanol. Magnesium 2+ is larger and less polarizing, so MgCl2 is much more ionic, with higher melting point and much better behavior in water than in organic solvents.
If a white precipitate dissolves in excess sodium hydroxide, that points to an amphoteric hydroxide. So solution X contains beryllium ions. Be2+ first forms BeOH2 as a white precipitate. Then in excess hydroxide, it dissolves to form the soluble complex ion, often written as tetrahydroxoberylate, BeOH4 2-. Solution Y contains magnesium ions. MgOH2 forms as a white precipitate and stays insoluble in excess sodium hydroxide because magnesium hydroxide is basic, not amphoteric. Group 2 oxides are generally basic, so with water they form hydroxides. Magnesium oxide reacts with water to form magnesium hydroxide, but because MgOH2 is only slightly soluble, you often see a suspension and only a weakly alkaline solution. Calcium oxide reacts much more noticeably. It forms calcium hydroxide and releases heat, giving an alkaline solution. With dilute hydrochloric acid, the reactions are straightforward acid-base neutralizations. The oxide dissolves, producing the chloride, salt, and water. For example, MTO plus 2HCl gives MgCl2 and water. To compare oxides and chlorides, group 2 oxides have very high melting and boiling points because they form strong ionic lattices between M2+ and O2-. The oxide ion is small, so the electrostatic attraction is strong and lattice energy is high. Chlorides have lower melting and boiling points than oxides because chloride ions are larger, so attractions are weaker and lattice energies are lower. Also, beryllium chloride is a special case with significant covalent character, pushing its melting point even lower. Down the group, chlorides become more ionic as polarizing power decreases, so their melting points tend to increase. To distinguish calcium from magnesium, ammonia is a simple choice. Magnesium forms a white precipitate of MgOH2 because its hydroxide is less soluble, while calcium usually shows no visible change because ammonia does not supply enough hydroxide to exceed the KSP of CaOH2. To distinguish calcium from barium, use sulfate ions, either dilute sulfuric acid or sodium sulfate. Barium gives a dense white precipitate of BaSO4 immediately because it is extremely insoluble, while calcium sulfate is much more soluble, so you may see no precipitate or only a slight one depending on concentration. Aluminium is protected in air because it rapidly forms a thin, tough Al2O3 film that prevents further corrosion. That same oxide layer explains why aluminium shows little or no reaction with cold water. In dilute acids like hydrochloric or sulfuric acid, the oxide film can be removed, and aluminium then reacts to produce aluminium ions and hydrogen gas. Aluminium is also amphoteric, so it reacts with dilute alkali, such as sodium hydroxide, to form soluble aluminate species like AlOH4- and hydrogen gas. Aluminum 3+ is small and highly charged, so it has strong polarizing power. Whether that produces covalent bonding depends on the anion. Fluoride is very small and not easily polarized, so AlF3 remains mainly ionic with high lattice energy and high melting point. Chloride is larger and more polarizable, so Al3+ distorts it strongly, giving AlCl3 significant covalent character and often molecular structures like the dimer Al2Cl6. So the difference comes from anion size and polarizability, even though the aluminum ion is the same. For magnesium with steam, the typical observations are a bright glow as magnesium reacts, formation of a white solid magnesium oxide, and evolution of hydrogen gas. The balanced equation is magnesium plus steam gives magnesium oxide and hydrogen. For barium and cold water, the reaction is very vigorous, rapid fizzing from hydrogen, noticeable heat, and the solution becomes alkaline because barium hydroxide forms. Finally, comparing beryllium and barium with dilute sulfuric acid, beryllium reacts very slowly or not noticeably because it is protected by an oxide film and is less reactive. Barium is intrinsically very reactive, but the reaction can slow down because insoluble barium sulfate forms a coating that blocks the acid. Summarizing the practical trends, with water, beryllium shows no reaction in cold water because its oxide film is strongly protective. Magnesium is very slow with cold water, but reacts with steam to form magnesium oxide and hydrogen. Calcium reacts with cold water to form calcium hydroxide and hydrogen. Strontium does the same more vigorously, and barium reacts very vigorously. With dilute hydrochloric acid, the general equation is metal plus hydrochloric acid gives the chloride and hydrogen gas, and the rate increases down the group from beryllium to barium. With oxygen, group 2 metals generally form the monoxide. 2M plus oxygen gives 2MO.
The reaction becomes more vigorous down the group as the metals become more reactive. With bromine, the metals form bromides, MbR2, and again the reaction rate increases down the group. Beryllium remains a special case because its halides have much more covalent character due to the strong polarizing power of Be2+. When asked again why beryllium behaves differently, the marking points are consistent. It's very small, and Be2+ has exceptionally high charge density and polarizing power. Beryllium is also relatively electronegative for a metal, has an unusually negative standard electrode potential, and it lacks d orbitals. Those factors lead to amphoteric behavior, increased covalent character in many compounds, hydrolysis of its salts to give acidic solutions, and distinctive reactions like methane formation from beryllium carbide.
To distinguish calcium and barium solutions quickly, add sulfate ions, sodium sulfate or dilute sulfuric acid. A dense white precipitate forming immediately indicates barium ions, because BaSO4 is extremely insoluble. If there is no precipitate, or only a slight one, calcium is more likely, because CaSO4 is significantly more soluble than BaSO4, so precipitation is less pronounced under the same conditions.
To wrap up, beryllium's anomalous behavior in group 2 comes directly from its small size and the strong polarizing power of Be2+, which explains amphoterism, covalent character, hydrolysis of salts, and methane formation from its carbide. Diagonal relationship is the broader periodic idea that certain period 2 elements resemble period 3 diagonal neighbors, because moving across and down the table produces opposing trends that can balance out. And in qualitative analysis, identifying magnesium, calcium, and barium relies on predictable precipitates and their solubilities, always supported with reasoning from solubility product, lattice versus hydration effects, and polarization.